This is a document that was contained in the document that Chesapeake gave to the Securities and Exchange Commission in 2010, and they use it in all their PowerPoint presentations. It contains everything you need to know and summarizes everything I've told you about geology of shale. What is it? Here's years. The number of years a well has been in production. So they've drilled the well, they fracked the well, they've had flow back, and at some point they say the well is in production. It's producing gas. And here is the volume of gas that that well produces each day. So this is millions of cubic feet of gas per day. And you can see on day one, this well, which Chesapeake claims was the average well, that's what they're required to show their shareholders in SEC. This is the production from our average well in Pennsylvania as of 2010. The average well produced 3.5 million cubic feet the first day. That's a lot. Let's see, back then, 2010, gas was selling at about $3 a thousand, 3.5 million. Divide by 1,000, let's see, 3.5 million, it's 35,000? Is that right, 35,000? 3,500. 3,500 times 3, that's $11,000 worth of gas first day. And if you had a 20% lease, you got 20% of that after expenses. So how much money are you going to make on that well if you're the leaseholder? Well, you want to know how much am I going to make the second day, the third day, the fourth day, the fifth day, at the end of the first year, second year. Look what happens. This is called a decline curve. Put together the last two slides I showed you. The gas that they can readily get is the gas that's already in the fractures that were caused by the gas. That's what comes out the first day and the first year. By the end of the first year, now the molecules have to travel 0.5 millimeter. By the end of the second year, they have to travel 1 millimeter. By the end of the third year, they have to travel 2 millimeters. And by the time you get out to the 10th year, that's the molecule that was that far away from the cracks and it's taken that long to get there. And that's it. There's your total experience for your well. At the end of the first year, your decline is about 70%. If you made $1,000 the first day of that year, on the 365th day of that year, you made $300. And then it's all downhill. Okay, well then how much gas will this well produce ultimately? Well, that's, you take the integral, for those of you who are calculus fiends, if you integrate that curve, you get this curve. This is the actual production. And what Chesapeake said is, we presume at the end of 10 years, this well will have produced a little under 2.5 billion cubic feet of natural gas. And at $3 a thousand, that's $7.5 million. Sounds like a lot, right? That well produced $7.5 million worth of gas when the gas was $3 a thousand. How much did it cost to drill the well? $5 million. How much did it cost to pay taxes on it? How much did the capital cost to borrow the money to drill the well? How about finding costs, dehumidification costs, processing costs, transportation costs, and royalty costs? What's the break-even price? When do you start making money? You certainly don't make any money the first day. You got to wait until you've produced enough gas times the price of the gas to overcome all your expenses. Then you start making money. Today, this well would not make a penny. That was the average well in 2010. Doesn't make any money. You getting the picture?
A well that's been fracked?
Yes.
Has been fracked. Okay.
This is the average.
Okay.
This particular well was actually in production, and according to Chesapeake, it represented the average of all the wells they had put into production in 2010. So there are wells that were better than this, and there were wells that were worse.
It's not making any money. Why do they want to?
We'll come to that. All right. Surprise, surprise. We now have about 30,000 shale gas wells in the U.S. Not 1 million, not 2 million, about 30,000. That's the entire industrial experience for all 600 operators that have been drilling for shale gas in the United States since 1990. 30,000 wells. That's the entire experience. No company has more than a few thousand wells of experience. And here's what they found out. Because of this picture, and because of that performance, they have found out that the recovery efficiency averaged over all the shale plays in the United States is 7%. What's recovery efficiency? Can I go? I have to go back a lot of pictures here, but it's important that I do. Recovery efficiency. I'll get you back where you belong, don't worry. Each one of these wells was accessing a block of shale. This long, roughly 2 miles. This wide, roughly 500 feet. This thick, whatever the thickness of the shale is, 100 feet, 200 feet. Right? You multiply length times width times height, you get volume. Remember that from high school? Companies know they can estimate the total amount of methane in that volume because they know the total organic carbon content of the rock. But I just got through telling you that just because the methane is there, you can't get it all out. You can only get the methane out that's either already in the natural fractures or very close to them. So now let's take this magical mystery tour again and get you to the data that you need to understand about how much of all the methane in each one of those blocks is currently being recovered. 7%. That's the efficiency factor. For tight oil, Bakken, Texas, 1 to 2%. This is another reason why this is different than conventional oil and gas. In conventional oil and gas, you're getting 70 to 80% of the resources down there because it's already accumulated for you in a pool. You get the straw to go into the pool, you get 70 to 80% of it. In shale, you get 1 to 2% of the oil and maybe 7 or 8% of the gas. Very inefficient process. All that ancillary infrastructure, all that 10 wells on a pad, all that clustered pad arrangement, all that pumping, and you get 7% of the resource. My grandchildren are crying. That is a resource. It's a national resource. And we've invented, the industry has invented, a technique that is inelegant and inefficient and wasteful. Once they do this, you can't go back a second time and say, can I get the next 7%? No, because you've injected water into the formation. Millions of gallons of water. And that ruins the formation. You get the 7% out? Excuse me?
Aren't there chemicals in that water? A lot of chemicals?
Sure. Yeah. We can talk about those too. The chemicals are necessary to get to 7%. Without the chemicals, you don't get anything. If you just pump water down there, you get nothing. All right. So that's the first myth. Let me summarize. The industry says New York should be doing what everybody else is doing. It's the same thing we've always been doing. No, it's not. There are 4.2 million oil and gas wells on the face of the earth. There have only been 30,000 shale gas wells. Have they all been fracked? Yes. Is it typical fracking? Absolutely not. It's high volume fracking with a concoction of chemicals that had to be invented specifically for this task. It's spatially intense, heavy industrial activity that goes on for a long time, blah, blah, blah. Let me move on to the second myth. If you suddenly found that your water well doesn't look like, smell like, or taste like it did yesterday, it was always that way. It was just your imagination. It wasn't us. At worst, it was a coincidence. Really? Are we willing to suspend disbelief for such nonsense? Do we really think that thousands of people around the country are simultaneously lying so that they can sue Big Exxon? Try suing Big Exxon. Try that sometime. See how successful you're going to be. That's the way they want us to believe. All right. So, leaking gas, well, it's a chronic problem. It's a ubiquitous problem. It's a well-understood problem. And it's unresponsive to tough regulation. And the rate of occurrence is increasing. I will prove each one of those statements with the industry's own data. First, what do we mean by contamination? Many of you have seen this chart. It comes off of a peer-reviewed paper done by colleagues at Duke University. They went out and they measured methane concentration in hundreds of water wells in Pennsylvania. Some of them very close to gas wells, some of them not close to gas wells. And they found what's called a correlation. Here's the distance between a water well and the nearest gas well. This is in meters. Here's the concentration of methane in the water wells. Naked eye says the closer the water well is to the gas well, the higher the concentration of methane. Industry says that's a coincidence. Well, it could be. From a scientific point of view, there's no causality here. We can't prove that the methane in this water well, okay, came from the gas well that was only 100 meters away. Can't prove it. Very difficult to prove. Never been proved in a court of law. That's something that the industry will never allow to go into a court of law. Situation like that gets settled. All right, the people who wrote this said, well, how did the methane get into the water wells? Remember, this is a scientific investigation. If the methane got into the water wells because it was coming from gas wells, how did it get from the gas well into the water well? That's a really complex question. First of all, you have to figure out how the methane got out of the gas well, because the gas well was supposed to be transporting the methane into a pipeline at the surface. Then you got to figure out whether the methane, if it got out of the gas well somehow, how did it get transported through rock to the water well? Those are really, very, very difficult and complex questions that are just now being studied. So let me show you what a leaking well could look like. And sound like. This is the production casing. That's the steel pipe, the innermost of the 4 layers of steel casing. That's the one that goes all the way down to the end of the well. That was that red line I showed you in that black shale at the bottom of the Canandaigua. It goes down 5,000 feet, goes out 10,000 feet, and the gas is supposed to be coming up the inside of that pipe. And up to the pipe goes into a pipeline, like a gathering line, where it then goes to dehumidification, compression, processing, and then goes to your gas stove. Obviously that well is leaking. Okay. Leaky wells go by many names. I worked with the industry for 25 years. I'm very familiar with the lexicon, the jargon, the camaraderie, the collegiality, the culture. Yeah, been there, done that. All right, what you're seeing here is called bubbling in the cellar. That's the exact phraseology that's used, bubbling in the cellar. You're seeing gas bubbles coming up in water that's collected in the cellar of the well. The cellar of the well is an area that's excavated around the wellhead for the specific reason of providing a telltale. If you don't see any bubbling in the cellar, you might think the well isn't leaking. No. We'll talk about that in a minute. But bubbling in the cellar goes by different names. Sustained casing pressure, sustained annular flow, sustained casing vent flow, loss of zonal isolation, and gas migration. Depending upon which paper you're reading, which conference you're going to, by the industry, they use different terminology. Nowadays, they call it wellbore integrity. Not loss of wellbore integrity, just wellbore integrity, implying that wells have integrity. But when you go to the workshops on wellbore integrity, all they're talking about is the loss of wellbore integrity. But to the casual journalist, oh, the industry's having a conference on wellbore integrity. They're talking about how their wells have integrity. No, they're talking about how their wells don't have integrity, but it's all in a word. So how common are failures like this? And this is just one manifestation of a well failure. So you can go to a very reliable source like the Columbus Daily newspaper, and they have a headline last year that said, "Gas leaks from shale gas wells are rare." I didn't believe them. So here's industry data. I'm going to show you a lot of it. Don't fall asleep. Bar chart. This is offshore Gulf of Mexico well data collected by many different operators in the Gulf of Mexico over a period of many years. What it shows is, depending upon how old the well is, the percent of the wells that are leaking, this is sustained casing pressure, the well is leaking. If the well is brand new, 5% of the wells are leaking. If the well is about a year old, about 12% of the wells are leaking. If the well is about 10 years old, about 40% of the wells are leaking. When the wells are 30 years old, 60% of the wells are leaking. It's not rare. But this is not shale gas. This is not even onshore. This is offshore, non-shale gas. So maybe this data is inapplicable. And I'll buy that. From a scientific point of view, I would not buy that. I would say, show me more. 2009 paper, SPE, a Society of Petroleum Engineers. I'm a member. These are two very, very well-known researchers. And they went to Western Canada and looked at data for 340,000 onshore oil and gas wells in Canada. It's knockoff of Mexico. Some of these are shale gas wells, a very small number of those 340,000. Most of them are fracked, but non-shale oil and gas wells. And what they find is that depending upon how old the well is, the rate of failure keeps going up. In other words, brand new wells in 2005 were leaking somewhere around 2%. By the time those wells were 20 years old, they were leaking at 10%. It's not rare. They also went into a section of Alberta where they were doing deviated wells. Most of this data was for vertical wells. They went to a section of Alberta where there were deviated wells, and they found that deviated wells were leaking at the rate of 65%. Industry data. More industry data. Went to a webinar last year. The title of the webinar is Wellbore Integrity. Global well population that this engineer looked at was 1.8 million wells. He estimated 35% of them were currently leaking. Not rare. Go online to George King Consulting. He's the king, pardon the pun, George King is the king of consulting in oil and gas for leaking wells. His company determines whether your well is leaking and tries to fix it. This is his data. Notice the pattern? Does it look familiar? Young wells, somewhere between 0 and 5%. By the time the wells are 5 or 10 years old, 10 to 15%. By the time the wells are 35, 40 years old, that up to 30, 35%. So it's not rare. But again, I've shown this data many times, and I always get the criticism if you're not looking at current practice onshore in modern shale gas wells in a state with tough regulations. I'll accept that criticism. All the data I showed you so far was not exclusively from modern shale gas wells using current technology, current methods, current cement, current casing, in a state with the tough regulations. So what do? We went to Pennsylvania, did our own study. Now I'm going to show you data that's not from the industry, it's from me. And I've got to warn you that everything I'm going to show you for the next 5 minutes is not yet peer-reviewed. It's currently under peer review for the Proceedings of the National Academy of Sciences. I'm confident that it will be accepted, but I can't guarantee it will be. So take that for what it's worth. So we went to Pennsylvania and we decided to do really good science. Instead of looking at just shale gas wells in Pennsylvania, we looked at every single oil and gas well that was drilled in Pennsylvania over a period of 13 years. Because we wanted to see whether there was a difference. Were the old wells leaking at the same rate as the new wells? Were the shale gas wells leaking at the same rate as the non-shale gas wells? Were gas wells leaking at the same rate as oil wells? Were the wells in northeastern Pennsylvania leaking at the same rate as southwestern Pennsylvania? That's exploration space. That's what scientists love. You can ask all these wonderful questions, and depending upon the answers you get insights. No one had ever done this. So we looked at 41,000 wells over 13 years. We mined all the data, and the data is publicly available. You can repeat this experiment. Mark of a good science paper is one in which somebody else can do the same experiment you did to see if they get the same answers. So do it, and start tonight. Go home tonight, log on to the PATEP, download a couple hundred megabytes of data, and go at it. Took us 2 years because of reasons I'm going to show you. I'll show you. So we mined the data. How do we know whether a well is leaking? Well, the only thing we have are the inspection reports. Wells have to be inspected by inspectors. If there's no inspection report, we have no information. If we have an inspection report, we might have information. Okay? So we look on the inspection reports, and on the inspection reports is a box that can be checked for a notice of violation. If the inspector goes to a well and notices a violation, she checks the box and then notes which violation it is. There are hundreds of possible violations, many of them pertaining to leaking wells. So naively we thought, well, if we just look at all the inspection reports for all those wells, and we count the number of wells that were inspected and found to be in violation of leaking ordinances, we'd have the number of wells that were leaking, and then we can do all this data mining, and how naive. What we found out was a couple of things. Number one, of those 41,000 wells, 8,000 of them have no inspection records. Which means either they were never inspected or the inspection records had never been made public. We don't have any information about those wells. So 1/5 of the data, out the window. When we looked at the inspection reports, we wanted to make sure we were looking at quality information. Nothing we can say here can be of any higher quality than the quality of the inspector's report. We're not making anything up. We're reporting to you what he or she reported to us. We found out that at least 5,000 inspection reports were in poor shape, meaning either they couldn't be read or the date on them preceded the date on which the well was drilled. Okay, so you throw out bad data. That's what science does. If it's garbage, you can't use it. Still, we were left with 27,000 wells and 75,000 inspection reports. It's a lot of data. Then we noticed that just because a well was leaking doesn't mean it's going to get a violation. Wells get free passes. Just like we do. We're driving down Route 20, 70 miles an hour in a 55 mile an hour zone. You see those red and blue lights. The cop pulls you over and says, don't do it again. Doesn't he? Free passes. Inspector says, well is leaking, bubbling in the cellar, sustained casing pressure, sustained casing, annular flow, no violation. Naughty, naughty. Next time I come back, this better be fixed. That's okay. I can accept that. Except he won't be back for a few months. And the well might have already been leaking for 4 years. And during that time, what's happening to the water table? So we got smart and we literally read every inspection report for the comments. So an inspector is allowed to write comments, including, in addition to checking boxes, they're supposed to write comments. What did they see? What did they smell? What did they hear? And many inspectors, not all, are very diligent. They write essays. I'd like to have them as graduate students. Some inspectors never write a damn word. You learn nothing from those. So here's what we learned when we just filtered. We checked all those inspection reports, which ones actually had notices of violation and what were they violating. Well, we found 101 cases where the companies failed to report defective, insufficient, or improperly cemented casing within 24 hours. In other words, if a company knows their well is leaking, they got 24 hours to tell us. Does this mean that they got a violation because 24 hours and 1 minute after the well started leaking, the inspector found it? No. It means the well could have been leaking for months or years until the inspection occurred. Which raises the question, how often are wells inspected? All right. We found 76 cases of improper casing, found 81 cases of excessive casing seat pressure, and then we went on and said, okay, let's look at all the inspection reports where there are no notices of violation. And we found 69 cases of sustained casing pressure. We found 20 cases of annular gas, 34 cases in which a well had to be repaired by a process called cement squeezing, and the only reason you'd ever repair a well for cement squeezing is if it was leaking. So you add up all that stuff and you now have data on which you can perform functions, like asking really important questions. So now I'm going to show you a set of graphs that we derived from all that data. Stay with me here a minute. This is pretty fancy stuff. I'm not expert in probability and statistics, and I'm not expert in risk analysis. With data from over 27,000 wells and with 75,000 inspection reports, we can now do what's called risk analysis and ask, how long would it take the average Marcellus shale gas well in Lycoming County to start to leak? How can we do that? Because we have inspection records for hundreds of wells in Lycoming County at different ages. We can now extrapolate and do a risk assessment. That's prediction of likelihood. So here you go. This is weeks. How long you want to extrapolate into the future. And this is the probability of the well leaking. And in this case, we looked at all the wells in Pennsylvania that were drilled after January 1st, 2009, all over Pennsylvania, and we divided them into two categories. Shale gas wells, that's blue. Non-shale gas wells is red. And what we find is that if you're willing to wait 2 years, statewide, you should expect about 12% of all the shale gas wells to be leaking. Totally consistent with previous industry experience. On the other hand, if you wait 2 years, you're only going to find about 4% of the conventional wells leaking. Now, why in the hell is that? A well is a well is a well. You drill a hole, you put casing in it, you put cement in it. It doesn't, the cement and casing don't care whether it's a shale gas well or not. Why would we see this statistically different, statistically meaningful difference? Keep going. What's different about shale gas wells and conventional wells?
Deviated.
They're deviated, higher pressures, they're rushed in their construction. What makes you think that the conventional wells were still being inspected? Ah, wait a minute. No inspection, no information. Okay, and we have the dates of the inspections, and what we found is that because of the proliferation of shale gas wells and the quick activity to bring the shale gas wells onto the line, and the DEP wants to go inspect those wells because those are the ones that the journalists and Josh Fox are looking at, they stop inspecting the conventional wells very often. Then we said, is there any difference across the state? So this is a comparison of northeast counties in Pennsylvania to non-northeast counties. And here's what we mean by northeast. 1, 2, 3, 4, 5, 6, 7, 8, 9. The counties along the Pennsylvania-New York line. Red, those counties, blue is not. See a difference? If you're willing to wait 8 years for all those wells that have already been drilled in those counties, you should expect about 50% of those wells to be leaking. 5-0. Industry says we're learning as we're going along. You have to give us a chance here. You know, we're always improving our processes. Every well we drill, we're learning more. Oh, come on, you drilled 30,000 of them already. Okay, let's see if that's true. So here are wells that were drilled before 2009, and here are wells that were drilled after 2009 in those northeast counties. What you notice is that the rate of failure for the newer wells is higher than the rate of failure for the older wells. Industry is not right. They're not learning. They're getting worse. Why? Price of gas has dropped off the end of the table. They can't afford to wait so long on the cement. They can't afford to hire really good companies to come in and drill and case and cement. The workers, they really want to make a lot of money, are out in North Dakota and Texas. And who the hell wants to work in Pennsylvania in the middle of the winter? Okay. That's a summary of what we found. At least 13% of all oil and gas wells drilled in Pennsylvania since 2009 will fail. At least 45% of the shale gas wells drilled in northeastern Pennsylvania will fail. And what I just said, the newer wells are going to fail at a higher rate than the older wells. That's the reality. All right. Next myth, last one we're going to have time for tonight, and then we'll get on to those really great questions that you asked at the beginning. Methane is a clean fossil fuel. Let's make sure we understand the meaning of the word clean. The word clean here doesn't mean dirty, as in on your hands. When the industry says it's a clean fossil fuel, they mean with respect to climate change. That's the meaning of clean here. A clean fossil fuel is one that, compared to another one, has less effect on climate change, greenhouse gases. So originally, industry was saying methane is a clean fossil fuel, which would mean literally it has no effect on climate. Well, that can't be true because it's a fossil fuel. When you burn it, you get carbon dioxide. So it can't be clean. And so they backed down and said, okay, so it's cleaner. Cleaner than what? Cleaner than coal. Cleaner than oil. True, from a carbon dioxide perspective. And then they got backed into a corner because a couple people at Cornell said, but carbon dioxide isn't the only greenhouse gas. How about methane? Oh. So, again, we'll use really good data. This is from the National Oceanic and Atmospheric Administration, a government agency. And this is a graph that shows the concentration of carbon dioxide in the Earth's atmosphere as a function of year. And as you well know, last year we reached 400 parts per million. Carbon dioxide concentration in the atmosphere keeps rising because of the burning of fossil fuels. Natural gas is a fossil fuel. You burn it, you produce carbon dioxide, and the burning of natural gas contributes to that rise, just like the burning of oil and coal. That's incontrovertible. That's exact, precise science. Nobody can argue with that. But natural gas is methane, CH4, for those of you who didn't know that. So when you produce, process, dehumidify, compress, store, transmit, distribute, and burn methane, here's what happens. You produce CO2 when it's burned, less than you do when you burn an equivalent energy amount of coal or oil, absolutely true. But methane itself is purposely vented and accidentally leaked during the whole process. From the time they drill the well to the time the gas comes into your house, some of it leaks. Some of it purposely, vented for pressure control. Third thing that happens is when you burn it in processing, you produce black carbon, also known as soot. Same stuff you see when you burn diesel. So those are three bad things. It's a triple whammy on methane. Well, how much leaks? If this is all negligible, then we can agree with the industry that of all the fossil fuels, from the point of view of climate change, methane's the cleanest, because we would only have to worry about carbon dioxide. If we didn't have to worry about methane and we didn't have to worry about black carbon, I would agree. We should all be using methane. Heat our homes, drive our cars, generate electricity. It would be the cleanest fossil fuel. We'd still kill ourselves with climate change, but that's okay, I guess. The problem with methane is it's also well known. This is incontrovertible science. The consensus science is issued by the Intergovernmental Panel on Climate Change, which issues a report about every 7 years, which is the consensus science report, which says hundreds, in some cases thousands of scientists have debated the literature, looked at all the peer-reviewed literature, and here's what they revealed to us 4 months ago. Methane is a potent greenhouse gas. Depending upon how long you want to wait, if you want to wait 100 years, it's 34 times more potent than carbon dioxide. 1 kilogram of methane does as much heating in the climate as 34 pounds of carbon dioxide. If you only want to wait 20 years, the factor is 86. It takes 86 pounds of carbon dioxide to do the same amount of heating in the atmosphere of 1 unit of methane. Which means that over a 20-year period, which I'm going to convince you is the most important, who cares about 100 years? We're all dead. Not only dead by age, but climate change will have made life unsustainable in 100 years. So we should be worried about the next 2 decades, which means we should be using this number, which means if only 1% of the methane that comes out of a well leaks, it's the same thing as burning it twice. Small amount of leakage has a huge effect because of that number. It's a multiplier. Basic chemistry.